Okay, with that, thank you, Dr. Kumar. We will go over to our next speaker on the agenda, which is the paper Shurendher Kumar, Sampathkumar. I hope I'm pronouncing it correctly. The paper
Dr.
with Dr.
Kumar.
Dejung
Yeah,
Joy. There you
that's
are.
correct.
Okay, so please go ahead.
Sure, Miss. Can you able to see the screen? Oh, that's all. So,
That's just
hello
in
all.
presentation mode because we see
Oh,
your screen together with your notes. Oh, that's better. Thank you.
um, hello all. My name is Shurendher. So, I am a master's student at UC, and I am part of Dr. Dong Kim's research group. So, I'm excited to present this topic, which is also a major part of my master's thesis. So to start, autonomous mobile robots or AMRs are becoming increasingly common in both public and industrial spaces. They are expanding rapidly from warehouse to more uh, public settings like restaurants and airports. So this widespread adoption is a testament to the rapid growth in AMR usage. So which is evident when we take a look at the market's overall trajectory here. So, in 2024, in 2024, the market size is projected to hit around $20 billion mark, and by 2028, it's expected to double to nearly 40 billion. So, there are several challenges to deploy these AMRs, especially in human dense environment. First, integration process for AMRs into existing infrastructure can be quite lengthy, as we see in figure 5. So another major challenge is the high cost of implementation, as depicted in figure 6. And perhaps the most critical challenge, especially in human rich environment, is ensuring the safety and uh, navigation accuracy. This means that a robot must be able to uh, accurately detect obstacles, predict human behavior, and avoid collision. So, as shown in figure 7, the most common cause of AMR accidents are related to perception errors, prediction failures, and collision, both with objects as well as humans. So, this challenge highlights the need for more advanced navigation system, particularly in human-rich environments where safety and comfort are most important. This is where the concept of human-aware navigation comes. So, human-aware navigation or HAN is designed to allow AMRs to anticipate human behavior and operate safely in shared environments. Unlike traditional system that merely focus on efficiency, HAN prioritizes human safety, comfort, and social norms to ensure smoother interaction. So, let's take a look at the 4 features which make up HAN. So the first one is prediction and perception, in which Han excels in interpreting human gestures and movements. So by predicting human behavior, AMRs can anticipate potential collision and ensure smooth navigation. Next, in acceptable path planning, AMRs respect personal space and social behavior. For instance, they avoid approaching humans from behind or navigating too closely. So this adherence to social norm ensures that AMRs not only function effectively, but also move in a way that feels more natural and comfortable to humans. Finally, hand enables AMRs to adapt uh, on the fly, so to changes in the environment. So humans often move unpredictably, and this feature allows hand to handle more dynamic environments. So now that we have an understanding of what human hour navigation is, let's break down the specific rules that are particularly guided. Hand rules are mainly categorized into three main components: human safety, human comfort, and AMR naturalness, as shown in this figure. So first, let's talk about human safety. In everyday life, we instinctively avoid bumping into uh, other people uh, in crowded spaces by keeping a safe distance, right? So for robot, this means that it should respect the human boundaries and maintain a safe distance to prevent any possible accidents. So proxemics plays uh, a key role here. This is shown by the blue circle in the figure 9. So proxemics refers sorry. So proxemics refers to the invisible boundary of personal space surrounding the humans. This lets the AMR to maintain a comfortable distance from humans. So next, human comfort comes in. So human comfort ensures that AMR's movement don't cause any stress or discomfort to humans. Um, for example, imagine sitting in a cafe. So, and if someone walks too close behind you, it could be startling, right? So, similarly, if a robot navigates too close behind a person or within a person's field of view, it could potentially cause stress. So, backspace and field of view uh, are the rules directly related to comfort. So backspace shown in green ensures that a robot doesn't approach the humans from behind where they're most vulnerable. And field of view shown in gray ensures that a robot doesn't become a potential obstacle in front of the person. So lastly, we have AMR naturalness. This is about ensuring that the robot behaves in a way that feels intuitive and natural to humans. For instance, in shopping mall, if an AMR moves smoothly, yielding appropriately in a crowded area, it behaves more like another human and it feels less awkward. So, um, although there are like vast number of rules in this research, as seen in Figure 9, we focus specifically on three hand factor: proxemics, backspace, and field of view. So in this slide, we focus on how human hour navigation rules and the static obstacles are modeled using cloud points, creating a structured perception for the AMR to navigate safely and efficiently. First, let's take a look at the AMR dimension. It has a width of 1 meter, and it also has a safety buffer of 1.5 meters. This buffer acts as an additional precaution to uh, take into account any sensor uh, accuracy issues. And the AMR also has a sensing range of 25 meters, which is the maximum distance where the robot can detect any obstacles or humans in its environment. So now let's dive into the hand rules and how they are modeled as virtual cloud points. These virtual cloud points function similar to how a 2D LiDAR sensor captures its surroundings. So this enables the uh, AMR to maintain safe distance and avoid moving too close to humans. The dimensions of the hand factors uh, as like proxemics range of 4 meters are derived from literature. In a in a similar fashion, we also model static obstacles, mainly circular and rectangular obstacles as clue points. So now I would like to explain the potential field-based path planning approach. So in its simplest form, potential field approach works by combining two forces. The first one is attraction towards the goal by an attractive potential field and repulsion from obstacles through a repulsive potential field. So one of the most widely used methods in this category is artificial potential field or APF as shown on the left side. So here the attractive force is denoted as FA and the repulsive force is FR. So when we sum it together, we'll get uh, a total potential field FT, which guides the AMS movement. However, the APF suffers from two critical challenges: local minima and goal not reachable due to uh, obstacle nearby, which is more commonly called as GN. This first, local minima occurs when attractive and repulsive forces are equal and opposite in magnitude, which causes the AMR to get stuck in a single position. The genre occurs when the obstacle is too close to the goal position, uh, which results in the repulsive force being too greater than the attractive one, preventing the AMR from reaching the target position. So to address this issue, we employ enhanced potential field in this work. So the repulsive field, so it has two key components. The first one is the repulsive field is adjusted to account for the influence of the goal, solving the Gendron issue. This is denoted by FRG. And second one is FRE, which rotates the direction of the repulsive field, preventing the robot from uh, getting stuck in a local minimum position. Uh, Finally, I'd like to emphasize the importance of the distance of influence, the scaling factor Ka, Kr, and the orders of potential. And so these highly influence the path taken by the AMR. So these uh, these parameters fine-tune the balance between the attraction and repulsion to ensure smooth and efficient navigation. So for this reason, in our initial approach, we employ genetic algorithm optimization to fine-tune these parameters of uh, APF. So genetic algorithms and evolutionary algorithm essentially it evaluates different possible solution across the search space and selects the best one based on a cost function. So before diving into the optimization process, let's break down how the an APF setup works. So uh, as uh, as we discussed earlier, that the total potential will consist of two main components: the uh, attractive field and the repulsive field. In this approach, each hand factor is assigned its own repulsive field as shown here. So each of this repulsive field also comes with its own scaling factor and orders of potential, which brings us to a total of eight optimization parameters as shown here. Now, the cost function that drives the genetic algorithm is designed to reduce the path length while ensuring that the AMR strictly follows the hand rules by assigning penalties. So we perform optimization for a particular scenario. In figure 12, we can see that the AMR's path represented by the blue line, the human placed at the center, uh, the human is placed at the center, remains static throughout the uh, experiment. What's crucial here is that the AMR successfully navigated towards its goal, demonstrating its effectiveness of the optimized coefficients. However, we encountered certain limitations in the form of local minima and the GN as shown in these figures. So additionally, while this approach did show success in navigating through this environment, where humans are involved. Uh, so it did not generalize well to multiple environments. So, uh, moreover, this framework was not tested in a dynamic environment or with static obstacles. Thus, while approach one laid a good groundwork, it highlighted a need for more adaptable or comprehensive solution. So, this brings us to approach two. In in this, we used enhanced potential field to overcome local minima and gene rot, as well as we incorporate fuzzy inference system, which provides uh, adaptive coefficients. This allows the AMR to better handle dynamic humans in unpredictable environment, something the previous approach really struggled with. So, but before diving into the fish design, um, I wanted to explain a little bit about how this framework is structured. So, unlike approach one, where each hand factor had its own repulsive force, in this approach we only focus on the nearest hand factor. So, for example, in Figure 15, the field of view region is uh is, is the closest to the AMR. So, thus the repulsive force is only computed for uh, this region. Similarly, the uh, obstacle generates its own repulsive field. So this setup means that now we have like three scaling factors: Ka for attraction and Kr and Kh for repulsion. To further simplify things, we kept the order of potential to two, and the repulsive scaling factors are expressed uh, as a factor of attractive scaling factor. So this is how the fuzzy inference system is designed for this framework. So it has three phases, and its outputs are like the scaling factor Ka and the coefficients mu r and mu h. So the uh, rules for this phases are set up uh, with a simple logic. So the AMR needs to speed up when it's far from goal, but it should slow down when it's near to human or obstacle. So in this work, we have used like two triangular membership functions as shown in figures 20. So in scenario one, we examine a simple environment that include two static obstacle, which causes local minima and GN rod and a human moving through in the middle. So as illustrated in so so as we can see in the video, the AMR is able to navigate through the obstacles, maintaining a safe distance from human without violating any hand constraints, as well as it was able to uh, overcome the local minima as well as the GN rod. So, however, this environment is fairly simplistic. So, it it although it was able to handle this scenario, we still need to determine if it can manage more unpredictable and dynamic environment.
You need to start concluding the talk.
Okay, so this setup has a little bit more uh, complex environment, and the AMR was able to handle the multiple dynamic humans as well as static obstacle. In the scenario tree, we tested a more realistic scenario like an airport, and it had multiple humans as well as some static obstacle. So as we can see in this video, it was able to handle the unpredictability and the static obstacles as well. So further, like to make the behavior of AMR more realistic, we also consider some kinematic equations and some energy constraints. This is mainly to to allow the AMR to allow the AMRs returning more effective while dropping the linear velocity as shown in this velocity profile. So
And
to
sorry
conclude,
to interrupt, but yes, good. Please conclude.
yes. So to conclude, we introduced an EPF-based human navigation framework successfully. It was able to uh, perform an acceptable path planning, and it was able to also dynamically adapt to complex environments. In the future work, we are training the FIS rules and the membership function using GA to improve its robustness, and also we could probably expand the hand rule sets, and we could also integrate it with a global planner and existing hardware frameworks. That's all.
Thank you very much. We don't have time for questions, but I would like to go on to the next speaker right away. Barnabas, you're up.